Is NASA hiding something about 3I Atlas? Today, we're talking to one of the greatest astronomers alive, David Jewitt. He's a professor of astronomy at the University of California, Los Angeles, the man who discovered the Kuiper Belt, the scientist who observed the 3I Atlas with the Hubble Space Telescope and made this picture. If anyone knows what's really going on, it's him. If there's a truth behind this mystery, you're about to hear it. Professor, first of all, thank you so much for being here. It really means a lot to me. Before we begin, I'd like to say that many of the questions come directly from my audience. They want to hear not only from someone knowledgeable, but from a professional astronomer who is actually observing 3I Atlas with the best telescopes in the world. Straight to the point, unlike many people who theorize and even calculate and speculate about 3I Atlas, you, along with your researching, actually used the Hubble Space Telescope to characterize it, right? Could you explain how that process works? I mean, is it something like picking up the phone, calling NASA and saying, hey guys, I need to use the Hubble telescope?
You have to propose for the time. Usually you propose ahead of time. So in this case, I proposed, I don't know when, maybe last year, and you say, hey, I'd like to use Hubble Space Telescope to look at an interstellar object that has not yet been discovered. and the objective is to try to measure the nucleus and see how big it is, and then to look with the best resolution that we can get at this thing. And your proposal is evaluated by so-called peers, people who are other scientists, often people who don't really know what's going on, or people who are actually competing with you and so are not particularly motivated to give you access to the telescope. So there's a bit of politics in there. And then if you're lucky, you get allocated some time. So I had this program set, ready to go, long before 3I Atlas was discovered. And then when it was discovered, I asked for the program to be activated. And the observations that we took were basically planned months, maybe a year ahead of time, something like that. So, you know, the objective is pretty clear. We want to measure the size of the nucleus. That's number one. To do that, we take a series of pictures with Hubble Space Telescope, and it's called the Wide Field Camera 3, WFC3, which is a pretty nice CCD camera. Field of view is a few arc minutes across. So once you know that you have the orbit of the body pretty well, then you can point the space telescope at it and take some pictures. The trouble is this year is that Hubble is falling apart. You know, Hubble is a very old telescope, and many of its has gyroscopes to understand where it's pointing and how it's moving. Many of those have failed. And so its ability to point at a moving object and follow the moving objects, moving relative to the stars in the background. And everything is moving because it's going around the Earth. The orbit period is an hour and a half or something around the Earth. It's pretty short because it's not very high. So the gyros are the big problem. And at first, we were told that we could not look at Atlas with Space Telescope because the gyros would not allow that. So that problem was overcome. There are people at Space Telescope who are expert in understanding what it can and cannot do. And they found very, very narrow windows when it was possible to look at Atlas. So the orbit period is, say, 90 minutes. Our observations were like in 2 minutes, only possible in 2 minutes out of 90. So most of the time is wasted. we got a few little snapshots, and from those we were able to do something interesting.
So let's address a big misconception head on. Some people say NASA is hiding something about 3A Atlas. But for example, the Hubble images were taken by you, right? So when people say NASA is hiding something, they're basically saying you are hiding something. Could you please help me finally demystify this idea that NASA could be hiding something?
In the US, we have a lot of conspiracy theories, as you know.
It's the same here in Brazil.
Oh, yeah? Many of them are in the actual government of the United States. Other people with theories about all sorts of crazy stuff. You know, I have a class where sometimes the students tell me that we never went to the moon. You know, all those moon pictures, but the Apollo pictures were faked. And I don't know what's going on. People like a good story, I think, but it is definitely not anything held back by NASA. So NASA is really nothing. It's a source of money, right? It gives money to some people sometimes to do things, but it gets money to build the space telescope in the first place and to run it, but they're not doing science. They provide a facility and they provide some money that may help people to use the facility. They're not doing the actual thing. The data, I have to say, our data were immediately public. Like the public could get them as soon as I could get the images. You can see everything that I've seen in the raw data, basically. You have to do a measurement based on the raw data if you want to write a paper about it.
Mm-hmm.
But it's not like, the data are showing anything different. Anybody can do anything with the data. That's the whole deal. So that's a good thing about NASA, right? They're just pumping this stuff out into the public domain. There would be no reason there's no mechanism and there's no reason to hold anything back. I mean, it's just crazy talk. So I know for a fact nothing in my use of space telescope has ever been held back by anybody for any reason.
It's good to hear directly from a research, right?
Well,
But about the size confusion, I mean, since the discovery of 3i Atlas, we've seen many different size estimates on the media, sometimes 40 kilometers, 20, 10, 1. It became chaos, creating a narrative that astronomers don't know its true size. And I've read your Hubble paper, and you show that we have an upper limit of about 5.6 kilometers in diameter. So could you clarify technically why less than 5.6 kilometers is the correct interpretation? I mean, how confident we can be with this estimate?
Right. So the question is, how do you measure the size of something when you can't go there with a ruler? So the basic way is we measure the amount of light that's reflected. And the argument is the bigger it is, the more light it's going to reflect.
Mm-hmm.
One problem with that is not just the size, but the albedo matters. So the reflectivity. So, two pieces of paper, a black one and a white one, would look completely different brightnesses because the white one would reflect more light. That's called the albedo. We don't know the albedo of 3I. We do know the albedo of regular comet nuclei, solar system comets, and it's a few percent. It's 4% or 5%. They're pretty black because they contain a lot of carbon. So I assume the albedo of 3I is 4%. And then I measured the amount of light reflected from 3I Atlas. Now the deal is, what exactly are you measuring? If you had a bare nucleus with no coma, no dust around it, you would truly be measuring the nucleus.
Mm-hmm.
But the problem is, it is surrounded, it's active, it's ejecting all this stuff. You are measuring light reflected from all the dust particles around the nucleus, as well as the nucleus itself. So if you ignore that fact and just measure the total amount of light, indeed, you get some big size, like 15 or 20 or 30 kilometers or something crazy. But we know that's absolutely wrong, because that's the light scattered by the coma, not by the nucleus. So the reason to use space telescope is to get very good angular resolution. We want to look down really, really tiny, really as close as we can to the nucleus, so that we can eliminate most of that dust from the coma and just get the signal from the nucleus. That's why we need the high resolution of space telescope. It's about 10 times the resolution of typical ground-based telescope, maybe even 20 times. So we get a lot closer to the nucleus. So we get a lot better estimate of the size. However, we have a model, we can figure it all out. We still did not detect the nucleus, even though we have the best possible angular resolution from space telescope. So we have a limit on the size, and the limit just says, if the diameter was bigger than about 5.5 kilometers or something, then it would make a bump in the middle of the image that we would see, a brightness bump. And we don't see that brightness bump corresponding to the nucleus. Therefore, the nucleus must be smaller than 5.5 kilometers, assuming the albedo is 4%. So that's the best estimate of the size still, and maybe for some time to come, that'll be the best estimate. My guess is much smaller still. It's probably a kilometer or even less than a kilometer across, something like that. It's probably not a big object.
Perfect.
But the early statements that it's tens of kilometers across.
It's because they are using the total light I mean,
yeah.
forgetting about the scattered light by the
And then it
comet.
gets picked up by one news outlet and then spread to another one. It gets bounced around.
Yeah, yeah.
Oh, it's a huge nucleus, and then it's going to hit the Earth, and it gets crazy.
Professor, your career has been dedicated to comets, more broadly, minor planets. I mean, you are directly responsible for the discovery of the Kuiper Belt. It's often said that the anti-tail of 3i is strange, and some people even claim this might indicate it's a spacecraft. What's your view on this? Is the anti-tail truly an anomaly?
No.
So,
No, it's not. So look,
so it's common in our solar
look
system.
at other comets. The
Yeah.
deal is the comets, a comet nucleus is sitting there, in sunlight. The sun shines on one side.
Mm-hmm.
The side facing the sun is the day side. That's the hot side. That's where the ice sublimates.
Yep.
So material comes off the hot day side. The night side is cold because it doesn't see sunlight, so it's cold, and it doesn't sublimate. So material initially is launched from the comet nucleus towards the sun. Okay?
Yeah.
So it's very common to see that. It's normal to see that. Material initially goes towards the sun, and then the sun is emitting light, and particles of light, photons, carry momentum, and when they bump into dust particles, they can push them back. So if you wait long enough, those particles that initially are launched towards the sun get turned around and pushed off into a tail. So the classical comet tail is indeed behind the nucleus, it's trailing behind.
Yeah.
But initially, the particles go ahead. So that's exactly what we have seen in Atlas. They have this plume going towards the sun, and then the particles got turned around, and later on, a month later, the tail appeared. So to say it's abnormal is not really true.
About the nickel iron topic, there was a moment when the media widely reported that 3i had nickel without iron. Later, we saw nickel with some iron.
Right.
Then came the idea that this could indicate a metallic surface or even some kind of alien ship producing an alloy. On my channel, I've been explaining that this nickel is coming from carbonyls. It's a gas, not solid metal. Could you clarify whether this nickel-iron ratio is truly anomalous or...
There's a weird story behind the nickel. So the nickel lines were discovered only a few years ago, maybe 5 years ago, in another object. But then it was found that actually all the spectra taken over the past many, many decades indeed show these nickel lines. So the nickel lines have always been there in different comets, but not identified until recently. So finding nickel is not something that distinguishes Atlas from regular comets. There is a certain ratio between nickel line strength and iron line strength, and it seems to be a little different in Atlas from most other comets in which it's been measured. But I think it's too early to understand what that means, if anything. It certainly doesn't mean that it's a metal comet.
Yeah.
These are atoms, free-floating atoms that came out of some molecule that was released from the nucleus. It's not an indication of the overall composition.
And what about the extreme negative polarization? This became like a major talking point online. People saw extreme negative polarization and immediately imagined exotic materials or artificial surface. But as far as I understand, polarizations depends on dust grain size, composition, porosity, scattering angle, observing geometry. So does it suggest anything unusual? What does this extreme actually represent? So, I mean,
when you look at those papers, a couple of papers, when you look at those papers, it's not that extreme. All it is a measure of probably is the porosity of the material. So again, we're not measuring the nucleus when we do polarization measurement. We're measuring the dust particles blown into the coma. And those particles are quite big on the average. They're like 1/10 of a millimeter across. That's way, way bigger than the wavelength. So there's a light particle, a photon goes in and it bounces around and it gets polarized while it's bouncing around in these very porous particles. So, okay, so this object is emitting fluffy particles, essentially, is what that means. Are they dramatically more fluffy than anything else ever seen? No.
In late October, about 3 weeks ago, I think,
Yeah.
the NASA JPL's Bulk Body Database page for the 3i was updated during the US government shutdown, showing parameters for non-gravitational acceleration. This raised a lot of doubts and conspiracy theories. People started asking, if NASA was shut down, how was this updated? In my own research, I found that this might be simply the result of automatic orbit updating algorithm that run independently of the shutdown, but people often ignore this kind of detail. But I want to hear directly from you. Could you clarify what this non-gravitational acceleration really represents, and especially, could the presence of a non-gravitational term ever be considered as an evidence for an alien ship, or is that a misunderstanding of what these orbital parameters actually mean?
So yeah, so again, comets routinely show non-gravitational acceleration. It means when you measure their position and try to fit it with an orbit, you cannot accurately fit it with a pure Keplerian orbit. So if you only use the gravity of the sun and the planets, you cannot explain the motion of the body. So you need some extra force, and that's the non-gravitational force. But the non-gravitational force is basically just recoil. It's like if I'm carrying a big boulder and I throw the big boulder off in that direction, my body will recoil in the opposite direction.
Yeah.
So the comet nucleus is ejecting material towards the sun and is recoiling in the opposite direction. That's the physical origin of the non-gravitational acceleration. It just means the mass loss from the nucleus is asymmetric, which is absolutely the way it is in comets, in all comets. Now, in the case of Atlas, we do not yet have a reliable measurement of the non-gravitational acceleration. And the trouble is, it's a really, really, really small effect, and it's a really, really difficult thing to measure. And it's difficult to measure because when you look at the comet, when you find the middle in a picture, you try to find the middle of the comet, we'll call that the center of light. The center of light may not be the same as the center of mass. So the nucleus is the center of mass, but the nucleus is ejecting all this dust. Most of it's going towards the sun, at least initially. And so the center of light is going to be off towards the sun relative to the nucleus. So that's a big, messy deal. And it's very hard to figure out where is the center of mass instead of the center of light. So it's always, always difficult to measure non-gravitational acceleration in a comet. In an asteroid, where there's a different possible cause for the non-gravitational acceleration, it's more simple, it's more easy. But for a comet, it's just a huge pain. And there are people who do this, that's all they do. And you have to throw away this measurement and that measurement, and we don't know what that means. And, it's a very, very difficult thing. Now, if you detect a non-grav acceleration, does it mean you have a spacecraft? No, because like all the comets have non-gravitational acceleration. Yeah. They're not all measured, but they all have it because they're all ejecting mass asymmetrically. So could it be a rocket ejecting asymmetrically? I guess, could be, but there's no evidence for that. It looks like a comet. Comets routinely eject mass asymmetrically, and they routinely have non-gravitational acceleration.
The way to distinguish like a rocket, an alien ship, from this normal non-gravitational, it would be math, right? Just to clarify, those parameters that showed on the website, so they are not measurements, they are parameters from a model just to maybe create some constraints that you're gonna use for the next observations, right?
Yeah, those are the parameters that they're like the deviations from a Keplerian orbit that you need to put in to represent the positions that have been measured, and so to make a more accurate prediction for where it will be in the future. But if you look to that, you mentioned that JPL webpage. If you look at that, it mentions the formal uncertainty on the non-gravitational, and the uncertainty is big. I mean, JPL is not lying. They have some number, but the uncertainty on that number is big as well. And so, in fact, they've changed the numbers from their first estimate. First estimate was no, that we don't see any evidence for non-gravs. Then they have an estimate for non-gravs. Now they have a different one. Other people who don't work at JPL have a different estimate for non-gravitational acceleration. So it's down in the noise. It's one of these things very, very hard to measure, and people have not yet got convergence on a reliable number.
One final question, Professor. I just find out that you're going to observe 3I again with the Hubble telescope, scheduled for late November, December, and early 2026.
November 30, yeah.
Yeah, it's a rare opportunity, right, to monitor 3I outbound trajectory. So what do you expect to learn from this new Hubble campaign? Are there specific signatures or behaviors you're hoping to detect? And finally, because this is important for the public, when you conduct this research, do you seriously consider the possibility, even as hypothetical, that 3I or other objects could be an alien spacecraft? Or this is not how scientific investigation actually works?
Well, it is. It is. So, okay, so the best example actually is from the first interstellar object, Oumuamua. So as soon as that thing was discovered, I was observing that. The telescope in Spain. And it has this light curve. It's a big, big light curve, right? It's like a up and down by a factor of 8 or something, brightness, which is very unusual. That really is unusual for the asteroids or anything else in the solar system.
It was tumbling, right?
It may have been tumbling, but it was certainly rotating.
Okay.
So that while I was observing, I actually remember looking at the data and thinking, that thing is about the size of a Saturn V rocket booster from the Apollo era, and it has about the same width to length ratio as a Saturn V rocket booster. So I thought, maybe this is a rocket. That's what I thought. Then I thought, well, it can't be a Saturn V because we know where they all are. They all fell back into the ocean. So that's not going to work. So maybe it's an alien thing. So yeah, I had that thought. Maybe it's an alien spacecraft with a big light curve because it's rotating over end. But, none of the other observations required that interpretation. And so I don't think that's the case. So to answer your question, yeah, anything is possible, right? You got to keep an open mind. Everybody agrees. Avi Loeb thinks that. I think that. All scientists think you should keep an open mind. But there's a famous statement that it's good to have an open mind, but don't let your mind be so open that your brain falls out, right?
Yeah.
That's something you don't have happen, and it might have happened in some cases. So yeah, I am open to anything, but if you have an interpretation like it's an alien spaceship, then you really need to be sure of that before you go saying that that's what it is, because you don't really know that without strong confirmatory evidence. Now, the observations that we have planned are in two parts. One is a little bit of the program that I've already published. We have 2 more orbits from that. And then I think we have 10 orbits for this new program to watch the object as it goes away. And there are many things we might see. The truth is, I'm one of those people who just likes to look at things to see what happens, right? So I actually don't know what will happen with 3I. One possibility was that it would break up near perihelion. It doesn't seem to have done that, but it could still do that because it's still fairly hot. It's still fairly near the sun. It still could break up, like Borisov, ejected a big particle or two. That could happen. Be interesting. It will fade out as it gets further away from the sun. The coma will drop down. If we're really lucky, the coma will go away completely, and we'll be able to take a picture that shows a bare nucleus. And then when we can see the bare nucleus, then we really will get a good measure of the size of the nucleus from the brightness of the whole thing. It'll become just like an asteroid. And we know this technique works well for an asteroid. It's just when you have a coma, it's more difficult to interpret what you've got. So if the coma dies off fast enough, then we'll be able to do that measurement. If the coma takes a long time to fade away, then the nucleus will also be fading away because it's moving away from the Earth and the sun. And then maybe the nucleus will be too faint for us to detect once the coma is gone. So that will be an unfortunate thing, but that's also possible. And then, you know, we haven't seen some things that we do see in comets. We haven't seen these rotating jets. So when you have a nucleus with an active source, it blows out material, and that material is curved like a rotating garden hose. It's like a sprinkler. It goes like in a spiral shape. We often see that in comets. I'm not aware of anybody seeing that in Atlas, but we might. That's still something that we might observe. That would be interesting because that would tell us about the rotation period of the nucleus. So there's a bunch of different things that we might get, but what we will get, I really have no idea. I mean, it's still really interesting, right? If it's not it doesn't have to be. It doesn't have to be an alien spaceship to be interesting.
Professor, thank you for helping us cut through the myths and get back to science. It's a privilege to hear directly from someone who is not only studying 3I, but actually collecting the data that will define how future generations understand this object. So thank you very much.
Thanks a lot for having me.
Curiosity is powerful, but evidence is what guides us forward. To everyone watching, remember, the universe is already incredible enough without needing to invent anything extra. Let's stay critical, stay curious, and keep learning together. See you in the next episode.